Welcome to Scale Up University. Welcome to Probability for Machine Learning course. So this is the lecture number 4 of module 2. So in this lecture, we will be discussing source of uncertainty number 2, that is incomplete coverage of the domain. So there is a common belief that if the train and test accuracy are high, the model should work in the real world. So it's a common belief that, okay, I trained a model and in the lab, it is showing some exceptional accuracy, like the train and test accuracy is very high. And then we get very confident that, okay, since it is showing very good train and test accuracy, the model is ready, it will rock. But in the real world, when you deploy it in the production, you see that many a times the model fails. Its accuracy, it degrades like anything. Like it its accuracy becomes very bad. It happens a lot. So in this lecture, we will learn that. So in this lecture, like at the end of this lecture, you will get a realization that why this happens and why this belief is wrong. And you will get an answer also to this question. So this belief is wrong. And for the reason for that is training data is never the word. So meaning to say that training data is always a sample of reality. Training data can never contain the entire, like all the set of possible values it cannot contain. So that's why we say that training data is never the word in most of the scenarios. There might be some exceptional scenarios wherein we can cover the entire domain, like the training data can be the word. But in majority of the scenario, training data is never the word. It means the model you are training. So the training data is a sample of reality. It is a subset. So model will not be exposed to many of the hidden patterns, many of the patterns. And during the in the real world, when you deploy the model, it might encounter those patterns and it does not know about those patterns. It has not got any training and hence it gives wrong results for those patterns. And this is because of which in the lab you might get very good training and test accuracy, but the same model, when you make it live, when it is in the real world, when you deploy it, you feel like you see that, oh, the model is not performing well, it is having accuracy issues. And because of this we can say that generalization error is unavoidable even with clean data and strong models. Even with clean data and strong models, generalization error is unavoidable. So this is a very important point I am like discussing with you. Like what is generalization error? The thing that the training data is a subset of reality. It is a sample of reality. It is a generalization error because training data is not the exact reality. So the model we will be training, it will be missing many patterns, many possible patterns. So this is the generalization error and it is unavoidable because the reality can be huge. Like the real world data can be in billions, but we cannot train in billions. The training data will have to be a sample of reality, and because of which we have generalization error. And here, one very important thing, no matter how hard you pre-process the data, no matter how much effort you put in pre-processing the data, like you removed all the ambiguities from the data, like you have a very clean data, even with the clean data and even with the strong models, like very good models, you will still have accuracy issues. And this is what many freshers they face. They feel like, oh, I put so much effort in pre-processing the data. I am using state of the art models. Despite of that, I am getting accuracy issues when I deploy the model. And the reason for that is the generalization error, because in the real world, the model is exposed to the full reality, exact reality. So it will be encountered with some patterns which it has not trained with, because training data is a sample, it's a subset of the reality, and because of that accuracy will suffer. So this is the main crux of this lecture. So in this lecture we'll discuss some very interesting points, topics. So first we'll discuss what does incomplete coverage mean. Like, definitely you got an idea, but we will get more clarity. Then we'll discuss training data is a sample, not reality. So training data is like a sample of reality. It is a subset of reality. It's not a reality. Then we'll discuss the long tail problem. It's a very important discussion we'll be making. Then we will discuss generalization, uncertainty, and the unknown future. Then we'll talk about distribution shift, and then we'll discuss why must models be probabilistic under incomplete coverage. So all these topics we'll discuss one by one. All the topics we'll cover in this lecture itself. So this is the lecture number 4 of module 2. Module 2 is uncertainty in machine learning. So in module 2, we are discussing uncertainty in machine learning. And this lecture is about source of uncertainty 2, that is incomplete coverage of the domain. And the first topic of this lecture is what does incomplete coverage mean? So incomplete coverage means the data set does not include all possible situations the model will face. The data set does not include all possible situations the model will face. So meaning to say that the reality has far more possibilities than any data set. The reality has far more possibilities than any data set. Like here, it's about the training data set I'm talking about. So when I talk about data set, I'm talking about training data set. Okay, so it will be like a combination of both training plus test, training plus test. So training data is a subset, not a mirror. So training data is a subset of reality, and it's not a mirror of reality. Mirror means exact replica. So training data is not a replica, rather it's a subset, it's a part. And because of that, since it's a subset, some regions of reality are unobserved, never observed. Now one more very interesting discussion we'll make. See, incomplete coverage is not carelessness. It is a mathematical inevitability. Because see, incomplete coverage is not like we are careless, it's like a constraint. Because see, the reality can be huge, it can be petabytes of data, and we cannot train the model. See, not every company has got resources like OpenAI, wherein it can like deploy GPUs. So computing, like it involves cost. So because of the resource constraint, because we have limited resources for computing, we have to limit the training data. And that's why it is a mathematical inevitability. So there are scenarios wherein despite of state of the art resources, despite of we having like huge resources, we cannot cover the entire domain. There are scenarios like that also, but there are scenarios wherein we can cover the entire domain provided we have sufficient resources, and that resources can be huge. So there are constraints are there, and because of that training data is a subset and it's not a mirror. And that's why incomplete coverage is not a carelessness, it's a mathematical inevitability. So let us look at one very real example. It will give you like some practical idea. If I talk about face recognition, so if I consider all the faces, like all possible faces, then it would be containing we will be having faces aligned at rare angles, occlusions, like faces with mask, helmet, faces with some cultural accessories like nose pin, earrings, or in India there is a concept of bindi. These are cultural. So these are like all possible faces. Now definitely we cannot consider all possible faces. Like for a single person also, at different angles, the pixel distribution will be different because the light falling, because if you change the angle of the face, the light falling, it will change a bit. So always, whatever training you will take, training images, it has to be a subset of all possible faces. So once again, see, the idea is that, let us suppose, what is face recognition? Face recognition system is basically, it will take a photo and it will tag a name to it. Okay, this photo belongs to this person. Oh, this is the face. The photo will be of a face, and the system will recognize the face. It will say that, oh, he is John, he is Sam. That is face recognition. Now, to train the model, now if we talk about all possible faces, it means, let us suppose for John, all possible faces means all the possible angles, because in different angles the light will fall in a different way. Or John might wear mask, he might wear sunglasses or spectacles, he might wear some cultural accessories, or he might wear helmets. So in like all possible scenarios, now unfortunately we cannot train the model considering all possible scenarios. It will be very complex. So we have to take a subset. So training images will be a subset of all possible scenarios. And this is leading to a incomplete coverage. So now what will happen is that you will train the model will learn many features about the John, the face of the John, for example, but it will still miss many of the possibilities, because reality has far more possibilities than the training images. And if in the real world, like in the production, like let us suppose you're passing the face of the John in some rare angle, and your model might fail to recognize it correctly because it has never seen those patterns. So this is the main crux. So the idea is that the data set is a window and it is not the word. So if a scenario never appears in training, the model must guess. Because if the model is exposed to a scenario which it has never seen during the training, then definitely it has to make a guess. And whenever the model will guess, there is uncertainty in the output, because the result, the prediction may be right or it may be wrong. So that's the idea. Now we'll look into the next topic of this lecture, training data as a sample, not reality. So all machine learning data sets, they are collected at a time, like at a particular instant of time you will collect it. So this discussion is mainly applicable for real-time data, because real-time data, continuously the data is getting generated. It is not possible that we can like capture it and train it there itself. So the data set we will be using to train the model, it has to be collected at a time instant. It is collected at a time. It is collected from some specific sources. All machine learning data sets are from specific sources and they are under constraints. So in short, we can say that they are samples from an enormous space. And since they are samples, we know that sampling introduces uncertainty. It makes sense. And why is it so? Because sampling does not cover the full reality. So there are some patterns are underrepresented and some patterns are missing entirely. If we look at a real world example, user behavior modeling. User behavior modeling. So the training data is past clicks, because we are trying to model the user behavior. So past clicks of the user and past searches. And if we talk about reality, new user might show up which the model has never seen. New users, new products, and changing interest. Like the model, it might be exposed to new users whose historic data we don't have. So in that scenario, the model will get confused. It will not be able to predict the behavior of the new user. Or let us suppose a new product is launched. So for new products, the model will get confused how existing users will react, whether they will buy it or they will like it or not like it. And changing interest, this is something very interesting, is because human behavior is very dynamic. Like let us suppose, like currently you might be interested in something, after 10 days you might be not at all interested in that. It happens a lot. Mood swings, or like user behavior is very dynamic. So changing interest, and because of the changing interest, there is a very big ambiguity, because the whatever the model will predict, it will predict based on the past records, past behavior. So here one very important insight we should take with us: the model always learns yesterday's slice of reality, not tomorrow's. So model always learns from the historic data. It will not learn from the future. Rather, it will try to predict the future based on the historic data. And in user behavior modeling, there is a very big mismatch, because user behavior changes with time, because there is a scope of changing interest. So whatever the model is predicting based on the historic data, it might be correct mathematically, but in reality, because the interest of the user has changed, the results may not match, and we may get puzzled, like why our model is not performing. So here we'll now discuss the asymmetry problem: finite data sets versus infinite real world possibilities. Now the data set size. So see, data set is always finite, the data set size. But if we talk about possible situations, they are effectively infinite, because real world scenario, the possible situations, they can be infinite. And this is the asymmetry problem, because the real world possibilities is infinite, but the data set we will be using for training, it has to be a subset, it is finite. So the asymmetry problem, a very big problem. No matter how large the data set, new combinations appear, new contexts emerge, and new edge cases arises. If we look at a real world example of this asymmetry problem, so nowadays these language models, like the large language models, LLMs, they are very famous. So in the context of this language models, even massive text data sets cannot cover every sentence, cannot cover every slang term, and cannot anticipate future phrases. So the idea is coverage grows linearly, but these possibilities, they grow combinatorially. Coverage is the something which our data sets will include. So coverage grows linearly, but possibilities is the real world possibilities. It is infinite and it grows combinatorially. So this is the asymmetry problem. Now we'll look into the next topic of this lecture, that is the long tail problem. So it has been seen that in most of the data sets, common events occur very frequently in the data set, and rare events, they are extremely sparse. Like in fraud detection, that we'll discuss very soon. See, most of the events will be not a fraud, because a fraud is something which will be very rare. So rare events will be extremely sparse. So in most of the data sets you will be using to train like AI models, you will see that common events will occur very frequently, and rare events will be very sparse. Like, and these rare events, they are often the important ones, like fraud, failure, safety. These are like rare events in data sets. And these rare events are often the most important because these are the events we will be predicting. So if we look at a real world example, that is a fraud detection. Now here 99.9% transactions are going to be normal because in the fraud detection data set 99.9% transactions on an average they are going to be normal, and only 0.1% transactions are going to be fraud. So here we can see that in the training data, because the we are discussing the distribution in the data. So the training data 99.9% transactions will be normal and only 0.1% transaction will be fraud. So here very clearly we can see that very few fraud examples in training data and many fraud types are never seen. So the training data will have like incomplete information about the fraud or very less information about the patterns related to the fraud data. And that is what is problematic. So 0.1% of fraud data and 99.9% of normal data. So this is like problematic. And this is the long tail problem, wherein what we want to predict here, we want to predict or detect fraud. And what we want to detect, we have very less information about that because we want more patterns to learn fraud. So long tail problem says that models are confident where data is dense and it is uncertain where it matters most. And this is the long tail problem. Models are confident where data is dense and uncertain where it matters most. Now we'll look into the next topic of this lecture, that is generalization, uncertainty, and the unknown future. So first we'll discuss the future problem, what it means. So even if you collect perfect data today, tomorrow introduces novelty, behavior changes. As we saw human behavior, humans can change interest and systems evolve. So the main idea is that, okay, whatever training we do, the training of machine learning models, we do it in like using the past data. So using the historic data, we train the model, and using that insights, the model will predict or forecast the future because model don't know what is there in the future, and that is the future problem. The future problem is that whatever machine learning model we are building, we will be training it using the past data, historic data. So the machine learning model will learn from the history, from the historic data, and it will predict the future. It will forecast the future. But it is totally unaware about the future. And the future problem is that the future is very uncertain because whatever patterns it learned, those patterns might be very different in the future. And the good example of it is the behavior change. Like, let us suppose you might be like interested in watching comedy movies, but after 2 weeks you might feel like you should watch a horror movie. So your interest got changed. So human behavior is very dynamic. So the future is uncertain. No one knew about COVID-19, and COVID-19 was something very unexpected and it changed everything. It was a very big reset. So future is uncertain, and that's the future problem we are talking about. Like, even you have collected the perfect data today, you trained the model, but tomorrow that model might not give you accurate results. That's the future problem. So unseen data is guaranteed. because time moves forward. So if you're dealing with real time systems or time series forecasting, so time is moving forward and we don't know about the future. So unseen data is guaranteed and reality is adaptive. Reality is adaptive. If we look at a real world example of the future problem, so if we talk about recommendation system, so this recommendation system, how it works is, so what is a recommendation system? It will recommend user some products and services based on the user behavior. So for a recommendation system to work properly, it should know something about the user, some behavior about the user, then only it can recommend. And that is the catch, because for new users or products, like new products or new trends, so whenever you feed new users, new products or new trends in the system will start facing cold start problem. And why it is a cold start problem? Because no history and high uncertainty, because no historical data exists. So the future problem, like we can call it like the cold start problem also. So we can say that cold start problems are a form of inevitable uncertainty. The first prediction is always the hardest. That's the crux of cold start problem. The first prediction is always the hardest. Now we'll discuss training versus test versus real world data. So if we talk about training data, so it is basically the data what the model learn from. If we talk about test data, these are basically held out data, held out sample from same distribution. So the idea is that we have a data set. In that data set, we like keep aside a chunk and we call the data set a sample. So held out sample is the test and rest of the sample is the training. And real world data is very different. It is basically the data to which the model gets exposed when the model is exposed to the real world. So real world data not guaranteed to match either. Now it's very clear that the test data we use to test the model in the lab, it can be very different from the real world data. So we can say that the test set is just a rehearsal. It's not the performance, because the performance will be judged in the real world. If we look at a real world example, like COVID era models, now most of the models were trained pre-pandemic behavior and they are failed when user behavior radically changed. Because see, as I discussed, COVID era is a reset. Most of the things changed. Even the user behavior, it got radically changed. So suddenly, all of a sudden, the models which were live, the models which were live, which were deployed, which were working very fine, which were showing very good accuracy just after COVID or during COVID, those models started giving wrong predictions, wrong results. Their accuracy suffered because of the, like it's a, like a very massive shift. User behavior changed. So many things changed. So this is the unknown future we are discussing, and this is what we are discussing, that real world data is the real testing ground. The test data you use to train the model is not the testing ground. It is just the rehearsal. The real world data you use is the real testing ground. And that real world data is unknown because the future is unknown. It is highly uncertain. We don't know what will happen tomorrow, what will happen next. So new novelty can be introduced. So we can say that generalization assumes stability. generalization assumes stability, but reality often violates it because the models which we assume to be stable pre-pandemic, because those models were showing good results, they were performing in the real world because they were showing very good performance with the real world data. So we were assuming that okay, now these models have achieved stability because they are giving very good accuracy with the real world data. Even those models, they like their accuracy got degraded because of COVID, like post COVID. So generalization assumes stability, but reality it often violates it. Now we'll discuss why generalization is uncertain in nature. Why generalization is uncertain by nature. So generalizations it relies on assumptions like patterns will persist forever, relationships remain stable, but these assumptions are never provable because these are like very uncertain assumptions. How we can say that okay, patterns will persist? Like we saw the example of COVID. The COVID it disrupted everything. All the patterns it also got changed. How we can say that relationships will remain stable? So these assumptions are never provable and they can only be tested retrospectively. If we look into one real world example, credit scoring. Now see, credit scores, you might know about it. So one very interesting discussion I'll make. See, credit scores, na, they depend on economic conditions. Now see, economic conditions is something which is very dynamic. Economic conditions change, like interest rates, employment patterns. Because economic conditions change, models trained in one economy may fail in another. So we can say that generalization is a bet. Rather, it's always a bet and it's never a certainty. And probability is how we cross uncertainty and not remove it. So probability is all about how to handle uncertainty, how to deal with uncertainty. Because see, it's very clear that generalization has to be uncertain. It's always a bet because generalization relies on assumptions which are not provable, which cannot be tested retrospectively. So generalization is always a bet. It cannot be uncertainty. It can never be a certainty. So we have to deal with uncertainty. We cannot eliminate it. So probability is about handling uncertainty, dealing with it. Now we'll discuss the next topic of this lecture, that is distribution shift. So see, distribution shift, it occurs when the data distribution changes with time. The data distribution changes over time. The model's assumptions no longer hold. So what is distribution shift? See, when the data distribution changes over time or when the model's assumptions no longer hold, then we say that okay, there is a distribution shift. And basically it occurs because of input changes. It occurs because of behavioral changes. It occurs because of environment changes. So let us suppose when a behavior changed, when the behavior is changed, all the assumptions will no longer it will hold because the model is trained on the past behavior. But when the behavior itself is changed, then the model, whatever the model has learned, it has become useless now. It will not hold. When environment changes, like the COVID-19 example we saw, even the models so these are like the reasons for distribution shift. So what is distribution shift? When the data distribution changes over time and when the model's assumptions no longer hold. And when distribution shift might occur, when input changes, behavior changes, and environment changes. So these are the factors for the distribution shift. If we look at a real world example of it, so vision production, like vision model in production. Vision means the computer vision. Vision model in production, computer vision. Now, if we talk about training, so let us suppose we trained the computer vision model in the lab, we trained it and we used daytime images. And when the model is deployed, when the same model which is trained using the daytime images in the production, it is exposed to images of nighttime, rain, and fog. So, here what is happening is the input is changed because the model was expecting daytime images, but unfortunately, the model was given nighttime images. So, input changed. Even the environment is changed because rain, fog, because while training, no rain, no fog, environment changed. And because of that, accuracy will suffer. So here what is happening is that the object is same object, but different distribution. So very important insight, a correct model can become wrong when the word changes. So this vision model in production is a very good example of it. Even the COVID-19 is a very good example of it. So here the model did not change, the reality changed. The reality did. Now we'll look into the last topic of this lecture, that is why must models be probabilistic under incomplete coverage. So see, we already saw that when we talk about incomplete coverage, there is a problem of long tail distributions wherein rare cases dominate error impact, meaning to say that the accuracy of the model will depend on the accurate prediction of rare cases, but that rare cases are very less in number, so it will dominate error impact. Edge cases in production. So when we talk about edge cases, like safety critical failures, unexpected inputs, it might happen in the real world and it might lead to some wrong results. Cold start problems. See, whatever we are discussing, it is because of incomplete coverage. The long tail distributions, edge cases in productions, cold start problem. So these are like result of incomplete coverage, consequence of incomplete coverage. And we already saw the cold start problem, wherein we have new users, new products, new trends, new domains. So now it's very clear that under incomplete coverage, we cannot claim certainty. It is impossible because when the training data in itself is complete, it's a subset, then definitely model will not be exposed to the reality. It is unaware of some very interesting patterns of the real world which it has not learned, and when it is exposed to that, it will be clueless what to do. It might end up giving wrong answers, and that is probably, and hence because of this incomplete coverage, models has to be probabilistic. And we already saw incomplete coverage is not about carelessness, it's about constraints. There might be resource constraints, there might be many factors which can lead to incomplete coverage. In some scenarios, even it is like mathematically inevitable to cover the entire domain. So it's very clear that okay, models have to be probabilistic under incomplete coverage. So finally, we completed this lecture in which we like saw in detail, like some good detail we saw, like the source of one of the source of uncertainties, incomplete coverage of the domain. So I hope you got very good insights from this lecture. So do subscribe to our YouTube channel, Scale Up University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.